Hi, my name is Landon Hicks, and here is Lab 1 of Physics 2211 on constant velocity. Alright, so introduction. We're going to go over the essential formulas and background knowledge needed for the experiment. We're going to analyze the pool ball in constant motion, which is my experiment that I'm going to be basing on its constant velocity. And then we're going to explain the composition of the computational model, which uses the initial velocity of that pool ball, and in an ideal world, will graph out the data as it should have been if there was truly no net zero force. And then we'll compare the experiment to the computational data. And then we'll look at the what if and what does it mean for this experiment. So, essential knowledge and formulas. The position update formula, it updates position based on the constant velocity of the object. Now, the velocity from time to time, meaning from one point to the other, will have an average velocity. We're going to take that average velocity times the time step multiplied by your added to your initial position will give you the position you ended up at. If we use that for enough steps, we can use the data points of where our position was to get the overall velocity of that motion, which will end up being essentially linear in this experiment as we stay at a constant velocity. Now, Newton's second law. It says that objects at rest will stay at rest, and objects in motion will stay at motion unless acted on by an outside force, meaning that if there is no net force acting on the object, it's going to stay at a constant velocity or stay at rest. This is described by F net equals your change in momentum over change in time, which you can manipulate to be F net equals ma, meaning that if you have no net force divided by your mass, you're going to have it's going to be 0 divided by some mass, meaning there is no acceleration. So, the experiment and the ideas behind it. So here is my pool ball, just a second of it moving, and the idea is for it to have constant velocity. If we look at our graph down here, we're going to see that it's relatively linear. It curves off a little bit as the felt of the pool table maybe slows it down a bit. Now, but the idea is that it only experiences gravitational force down and the normal force of the pool table onto the ball upward. Therefore, it would be balanced forces, keeping the velocity the same as its initial velocity. So let's look at the computational model. Now, in the computational model, I inputted what my initial position was at negative 0.43 meters and my initial velocity at 0.72. Now, I took the time step, my first time step in my experimental model. It was 0.033, that was my delta t between the time steps in my experimental. And then I saw how much did that position change. That position changed by 0.038 meters in that time step. So I did that for each and every time step, meaning it would have a exactly constant velocity, which it didn't have in the experimental model because it ended up curving off. So in this ideal computational model, we can see that it's perfectly linear. It ends up going a bit further than it did in my experimental model because it maintained its velocity the entire time. So let's compare these two models. As I was saying, we're going to see that the red line is drifting off because it does not maintain its velocity the entire time. So it's going to go a little less far than the ideal one where it keeps all of its velocity. This is likely due to the felt of the pool table pushing back on the ball, causing more friction with the ball than in an ideal model, maybe rolling this on maybe a glass pane. And then we can see that in the simulation, it's going to have that perfectly straight line and maximize the amount of distance with that constant velocity because it does not slow down at all, maintains an ideal constant velocity. So what if and what does this mean? How would the results change if I were to flip the axes? Flipping the axes would not change the motion of the ball because zero net force will always result in constant motion regardless of the direction. Meaning this could go negative, we could switch it to y and to y motion. It wouldn't matter because the net force will always have a linear motion, meaning that if you were to flip it, it would still be linear. It wouldn't change to maybe logarithmic or exponential or nonlinear in any way, meaning that it won't change in its slope or its derivative, and therefore it'll have the same motion and the direction is not meaningful. So is it possible to predict the amount of pushes and pulls it took to achieve the net zero force on the object? There would be zero pushes or pulls after the initial movement of the ball, In an ideal world, there are no forces that need to be addressed on the ball in order to make the object experience zero net force. So, meaning that if I don't push or pull the ball, if I had no forces to combat it, my force would inherently be net zero. Thank you.